Well, hi, everybody. Welcome to lab session 2 for MI260. Sorry, lab session 3. Gosh, we're moving through this semester. We'll go ahead and get started. The lab session for today, we're going to cover homework 2, which was really focused on meta-regression and using that atorvastatin data as our case study. Before I get started, though, I just thought I would ask if there are any questions based on the lecture materials from last week. I'll give you a minute to type a question in if you have one. Okay, well, it looks like there are no questions right now. If questions come up as we go through, we'll be pausing periodically to check and see if you've posted any questions. Feel free to post them as they come up. So for the homework assignment this week was only one problem. I was focusing specifically on trying to explain the between study variability that we saw in our analysis in homework 1 of the 80 milligram atorvastatin versus placebo data that we had in that data set. The homework focused on a number of questions that tried to elucidate I'll make this full screen here. Tried to elucidate what was causing some of the between study variability that we saw in our difference from placebo. We tried to do that first graphically with some funnel and radial plots that we'll use from the RMA package. And then we'll look at some scatter plots for two different covariates. The first was the baseline LDL in the study, and the second was the placebo response in this study. And then to try to give us some indication about which covariates, which one or both of the covariates might be useful covariates to put into a meta-regression model. Then we're going to fit the meta-regression model using the RMA function, and then plot that data using some of the forest plot capabilities in the metaphor package. And then we'll come back and fit a similar model using WinBUGS. So let's open up R and step through some of the solution code that I've put together. I'll post this on the course site as soon as we finish today. And I will blow up the font size here to make this a little bit easier to see. Okay, well, I think we're gonna I forgot we have this problem. We'll be able to see a good size font there in the console window, but not in the script window. But for the for the purposes of this, I hope that's okay. So the first thing we'll do is we'll again load our libraries, loading the metaphor, the R2WinBUGS, and the EMD book libraries. And then we'll set our working directory here to the directory where the data are stored. And that may be different for you. For me, that's in my E drive. All the data, as before, is in the MI260 USB folder, MI260 subfolder. And then these data are in the Fixed Effects hands-on subfolder. So for the first problem, we were simply asked to read in the data and to derive the difference from placebo. This is all identical to what we needed to do for the first homework, and so I'll skip over that. We did have one question posted to the training site about this standard error of the difference, and so maybe I can comment on that quickly. In this case, what I'm using is well, there are two ways to calculate the the standard error, we could make an assumption that the standard deviation within each of the groups is the same, and from that calculate a pooled standard error. And in some cases, you may have the information to do that. In this case, I'm not making that assumption about the common standard deviation on the response scale, and simply using the reported standard errors for the two change from baseline scores. Either approach would be fine as long as we're being consistent in how we're deriving that standard error of the difference. So we have our data set here, call it a TOR 80. And let's just take a look at that. This has our variable trial that identifies the trials, has the variable called, after we've done the data manipulation, a variable called diff, that is our difference from placebo, and a variable SE diff, that is our standard error of that difference. The covariates that we'll be looking at, I'll use LDL0 as my measure of the mean baseline LDL value. Strictly speaking, that is the LDL, baseline LDL value in the atorvastatin group. The baseline LDL in the placebo group is in the LDL0.PBO variable here. And we could just as easily use that as our as a covariate. Due to the fact that these are randomized studies, the differences between those within a study should be relatively small relative to differences between studies. So another option, if we really wanted to get maybe a better measure of baseline mean LDL, would be to take a weighted average of the two baseline LDL values from the two different groups. The other covariate that we'll look at is the LDL percent change from baseline in the placebo group. In our data set, that's labeled LDL PCFB.PBO. Those are going to be the two covariates that we'll look at. So the first question, and I see that I somehow have lost some of my code here. The first question said, use the funnel and the radial plots to in the metaphor package to make funnel and radial plots. So it turns out if you're interested, in order to use these functions, we need to first fit a model. So let's fit a model using the RMA function, and we'll let the response variable is diff, and the standard error is SE diff, and we'll use we'll fit two models. We'll fit first a fixed effects model, and then we'll fit a random effects model. So let's fit our, we need to put in the name of our data set here, a TOR 80. Okay. And we'll fit a random effects model just for the fun of it. So I'll cut and paste that, and all that we need to change here is FE for fixed effects to REML or DL for our random effects model. And let's go ahead and create that as fit2. So we now have two objects, fit1 and fit2, that are the fixed and random effects models for our difference from placebo. And if we simply wanted to create a funnel plot, we could say funnel of fit1, and I'll put a label on that to identify that this is from fit1. Okay, so we can run that code, and that'll make our plot here. Now, in this funnel plot, remember the data are the black dots, and the cone here is centered at the estimated mean value, and then the lines are corresponding to an interval in which we should expect to see 95% of these points. As you might expect, where that interval and where that cone is centered will or may depend on what the model fit is. So if we plot our fixed effects fit versus a random effects fit, we do get a slightly different picture. So if you watch closely the plot, I'm going to run this funnel plot for the random effects model, and you'll see that the cone shifts slightly when we do that. Well, that was hard to see because it flashed, but I'll leave this up to you to kind of look at it more closely on your systems. You can see that the cone moves slightly, but the overall inference doesn't really change. And so I'd ask you, based on this plot, would you deem that there is some sort of small study bias or publication bias? I'll give you a second to think about that. In the meantime, we'll make a radial plot. Okay, well, I think based on this plot, it's a little hard to tell given that there are so few studies. We have a couple of studies that are outside the prediction interval, but they, in this case, are balanced, one on the high side and one on the low side. So there's no, to my eye at least, there's no clear evidence that there's a difference or any evidence of bias, with the caveat that we have this effect that we have a relatively small number of studies to be basing that inference on. If you wanted to use a radial plot, you can just use the radial function. Again, the main argument to the radial function is a fit from the RMA function. And so the radial plot that we would make by default would look like this. This plot, if we're plotting the random effects model, notice that the standardized response variable here on what's called the z-axis is the data, yi, that's our difference from placebo, divided by the random effects standard error. So that includes the observed standard error plus the between study variance. The observed variance plus the between study variance, and the whole thing square root. And then plotted on the x-axis is the corresponding measure of precision. If we plot the radial plot for the fixed effects model, oops, sorry for that. What you can imagine is that we'll get a similar looking plot in that it's using the same mechanics, but what it's plugging in here is the fixed effects estimates and the standardized weights for the fixed effects model and the precision here from the fixed effects model. Again, this is the plot from the fixed effects model. Here's our plot from the random effects model. We can see with the random effects model, our prediction interval here is noticeably wider, as we would expect, because we're accounting for that between study variability. If sometimes I've found with these functions that you end up with a plot that's kind of small, or that it's hard to see the z-axis, I'm sorry, the circular axis here, which in the metaphor package is labeled as the y-axis. You can control the number of decimal places here that that are printed. You can also it helps to center the plot on the estimated response. And you can do that if we look at the help file here. You can see that there is an argument called center, and that would allow us to plot a centered version of the radial plot. And I'll show you what that looks like in a minute. You can also control the x limits, the z limits, which is the vertical axis. where your tick marks go, how many tick marks to plot on the circular axis or the y-axis, the color for the shaded region, and so on. But if we look at center equals true, let's take a look at how that plot changes. If we add here center equals true, we go from a plot that looks like, if we have center equals false, we have a plot that looks like this. When we move to center equals true, we end up with a plot that looks like this. And it simply rotated everything around, where now our y-axis here is the data. Sorry, I used y. This is the terminology for this axis is the z-axis, or the vertical axis is now our data yi minus the estimated value theta hat divided by its estimated standard error. So now that kind of expands this circular axis a little bit. It's just in effect rotating around that the previous plot, but it makes this a little bit easier to read. So if you're a fan of the radial plot, you can consider whether you like centered or non-centered plots. In any event, our inference here doesn't really change so much that there's no strong evidence of any small study or publication bias. Okay, I'll pause there to see if there are any questions. Okay, I'll keep moving ahead. The next question asked us to calculate the fixed effects estimate using the RMA function. Oops. That's not really right. This is left over. I'm not sure what happened to my copy of the homework here. I'll have to fix these things. The next question said to ask us to fit let's go back to the homework and see what it asked us to do. The third question now asks us to plot the mean difference from placebo against the baseline LDL as a scatter plot, and then to do a similar exercise using a forest plot. So what we have here is, let's see. Here we're going to plot our data using the scatter plot. This is a simple scatter plot. So we're plotting on our x-axis LDL 0, and on the y-axis the difference from placebo. And in this particular plot, what I'll do is I'll plot the points as filled in circles, and I'll relate the size to be inversely proportional to the standard error. So large or studies with small standard errors or a lot of information will get bigger circles than studies with small standard errors. If you make that plot, it looks like this here in the plotting panel. And again, with so few studies, it's hard to make much out of this plot, but it doesn't look like there's a strong relationship there between difference from placebo and the baseline mean LDL. Sometimes it helps to look at these as forest plots. And in this case, what we'll do is we'll first sort the data by the baseline LDL value. That's what these two lines here are doing for us. And then we'll make our forest plot using the forest function as we did last week. But we'll be taking advantage of this iLab option, which inserts an additional label to identify the points in one manner or another. And so here what I'm plotting is the baseline LDL rounded to 3 significant digits. And I can tell it where to put that on the plot using the ilab.xpos argument. And if that's a little hard to see, we can make it a little bit bigger. And so we have our, these are sorted by increasing baseline LDL. And again, looking at this, there's no obvious trend here in the observed data. So again, based on this plot, we'd probably say there's not much of a relationship between baseline LDL and the difference from placebo. Let's look at our second variable, which was the change from baseline LDL in the placebo group itself. And again, if we can make a scatter plot where the points are scaled based on the amount of information in them, we get a plot that looks like this. And this one maybe tends to lend to a little bit more of a trend than we had in the previous plot, probably largely because of this one point here, again, where we have a large placebo response as well as a large difference from placebo. So in this case, the placebo group went up substantially, in this case 7% or so, and there was a large difference from placebo. So if we look at that, again, using the forest plot function, we can get a similar sort of information, although a little bit less direct. We can see, again, a little bit of a trend here for the mean responses to become more negative or larger, farther away from zero, as the placebo effect increases, or placebo response increases. Okay, let's go back to our questions. So we had made our scatter plot. We made a forest plot using the iLab function. One of the questions was, which plot do you prefer? And does either variable seem useful as a potential covariate? I think we've answered the second question, that maybe this difference from placebo looks like it may be a potentially useful, I'm sorry, that the placebo response may be a potentially useful covariate. It's maybe a matter of personal preference for which plot you like. I tend to like the scatter plots a little bit better, particularly if we're allowing the scaling of those points to be related to the amount of information in those in the data. Yep. Okay. So we'll stop there and see if there are any questions about using either of these plots to investigate covariate relationships. Okay, if there are no questions, we'll move on to the next question, which was asking us to fit a random effects meta-regression model using first the covariates univariately, and then including them in both covariates into a model with a bivariate or multivariate regression. We'll step through how to do that using RMA, and then talk about how we might interpret the coefficients in this meta-regression. And thinking a little bit about the statistical and clinical meaning of, or significance of those. So the code, as we saw during the lecture last time, for fitting a meta-regression is fairly straightforward. It's very similar to what we have when we're fitting a standard meta-analysis, where the first elements here, the yi, the standard error or the variance, a call to the data argument, what method we're using, a study label, those are all the same. The only difference here is now we'll add in the argument mods, and we'll point it to a variable or variables in our data set. So if we fit a model using baseline LDL as a covariate, we'd simply say mods equals LDL 0. And if we were to fit that model and then look at the output, we'll see a number of things here. So first we see that we have, it provides us because we fit a random effects model, it gives us our estimate of tau squared and tau. And so we have a measure of tau here that's 6.8. And we'll come back and compare that to what we had without the covariate in just a minute. We have a test for residual heterogeneity. This is our Q, this is the kind of what would be a corresponding Q value for coming out of this meta-regression, telling us that there's still statistically significant heterogeneity if you like the Q test or Q statistic in the the test based on that. This test here is the test for whether or not there's a statistically significant effect of the covariates. In this case, we have one covariate, baseline LDL. As we get into multiple covariates, this is an omnibus test testing whether all of the covariates have a significant effect together as opposed to individually. And then our model results are down here telling us that we have an estimate of minus 30 or minus 31 for the intercept, and the estimate of the slope or the relationship between mean LDL, mean baseline LDL and difference from placebo LDL is minus 0.137 with a standard error of 0.3132. So very large degree of uncertainty relative to the parameter estimate. And if we were to look at a confidence interval, it goes from minus 0.75 to minus 0.48. Clearly overlapping 0 and giving us some indication that there's not a statistically significant effect of baseline LDL on the difference from placebo. If we were to fit the similar model, but now using change from baseline in the placebo group as our covariate, we would fit this model here called fit4. And all that we're changing here is what the mods variable is. And if we look at that one, we get a fit that is now has a residual between study standard deviation of 4.1. And if we compare that to what we had before, which was 6.8, we see a pretty meaningful drop in the between study standard deviation. So it gives us some evidence that we're explaining more between study variability with this particular covariate than with the baseline LDL. Again, our test for residual heterogeneity and test of the meta-regression covariate effect, overall test is plotted here. And our model results, this tells us now that for at a baseline placebo response of 0, we have an overall average effect of minus 55. And for every 1% increase in the mean placebo response, we get a difference from an extra 1.25% difference in the change from baseline, a change from placebo. With a confidence interval going from minus 2.5 to something that's just about 0. So think for a minute about how you might interpret these effects. I guess I've already alluded to that to some extent, but think about how you might interpret these effects using the principles we talked about in our lecture about the potential for ecological bias and how we need to be interpreting these at a study level rather than at a patient level. So what we would not want to do is suggest that if there's a individual placebo response increase of 1 unit, that an individual's, well, in this case it's hard to conceptualize, but individual's difference from placebo would be an extra 1.25%. Really, we're saying here that if the study level mean placebo response is an increase of 1%, that we would see a difference at the study level in means of about 1.25%. So this isn't the best example to be talking about ecological bias or the ecological fallacy, but hopefully maybe I'll come up with a better example as we get later into the semester. Let me stop there and see if there are any questions on using RMA. The next thing before we do that, I'll just show you quickly how to fit a model that includes both covariates. And in here, all that we need to do is C-bind them into a little matrix. And so we can put both the baseline LDL as well as the placebo response as covariates into the model. And if we were to do that and then look at fit 5, what we see is that we now have individual estimates for the two covariates that we have in our model. And this test of the moderators now is testing whether both of those covariates simultaneously are statistically significant. And again, if the estimated value of tau, the between study standard deviation, is really no different than when we just had the one covariate in the model. So all of these things might lead you to believe that the best model would be, when we're considering only these two covariates, might be a model that only has the percent change from baseline in the placebo group as a covariate. Before we move on to plotting, then I'll just check to see if anyone has any questions. Okay, the first question was, is it useful to center covariates in meta-regression? The answer is yes, and we'll see that when we get to the WinBUGS model. If we wanted to do that in these, we could simply put in here LDL0 minus the mean of a TOR $80 LDL0, and we could do the same sort of thing here for the placebo change from baseline. We could say mean minus the mean of LDL PC. Oops, TOR 80 LDL PCFB.PBO. If we do that, what we should see is that our estimate of the intercept has changed, but the estimate of the covariate effect has not. It does help. It does provide a useful, by centering, then we get a more interpretable estimate for the intercept in these models. As it turns out, for the covariate of percent change from baseline, the mean of that is fairly close to 0. Whoops. Let me undo what I just did there. The mean is fairly close to 0. It's 1.65. But that's substantially closer than the mean baseline LDL, which was around 190. So we'll see more benefit and more difference when we fit the model to fit 3 by centering the covariate than we did for fit 4. I have another question that said, the mean covariate in different trials are not that likely to be different, and thus perhaps hard to detect effects should be there. Is it possible to include information about the range of covariates in each trial in the model? That's a good question. I suppose you could conceive of including some measure of variability in the covariate distribution as a covariate. I'm not aware of any direct way to include that to, in some sense, enhance the power. Later in the course, we'll get into combining summary level data and patient level data. And when we get into those kinds of models, we'll see a substantial increase in our ability to detect covariate effects because the patient level data will be really providing that additional power to, or additional information to describe the covariate effects. As you point out, when we're simply working with aggregate data, the between study variability in the covariate means is typically fairly small. And if we were to look, let's go back and look at that. Well, here's the variability we see in our placebo responses, ranging here from about a 3.6% improvement to a 7.6% increase from baseline in placebo. That's probably a fairly wide range for something like that. If we look at the FIT3, I'll just make a sort of a crude plot of FIT3 here. Whoops. If we make maybe it's easier to see with the scatter plot. For the baseline LDL, we have a range of 175 to 205 or thereabouts. Again, that seems fairly wide, but obviously at the individual level, we'd get a much wider scatter of data. But to specifically answer that question, I'm not aware of any way to directly incorporate that into these models, other than maybe somehow thinking about both the mean and the variance as covariates, or the mean and standard deviation as covariates in a model. Good questions, thank you. So we've fit our covariate models. I sort of quickly gave you a glimpse of what it looks like to plot these objects. If we were to say we have our fit4 object, which is our model that uses the change from baseline LDL and the placebo group as our covariate. If we were to plot that, what we get is, we get the same kind of matrix of plots as we had before. If we focus in on the funnel plot, the forest plot, what we get overlaid here are these gray diamonds. And if in the hierarchical modeling sense, these are like, these are the IPREDs, well, these are the predicted values based on the covariates for each study. So these are the mean values for a study that has a covariate value equal to whatever that was in that particular study. So if I'll make a, the code for making a fancier version of that kind of labels everything nicely is here in this forest plot here. So here we have, so this gray diamond is a plot for a percent change from baseline LDL in the placebo group of 7.6. And this gray diamond is centered on the same prediction, but for a study that has a mean of placebo response of minus 3.6. So that's what we get if we kind of pretty up the default version of simply plotting that RMA object. This next question asks us to get predicted values at various levels of the change from baseline LDL in the placebo group, and specifically at a 2% improvement, no improvement, a 2% increase in baseline or change from baseline LDL, and a 4% increase. It turns out that there is a predict method for RMA objects. So if we simply say predict, give it the object name, and then give it the new mods option and pass in it the covariate values for that. In this case, it's one covariate, so we'll pass in a vector of covariate values. We end up with something that looks like this. We get, for each object, we get the predicted value, a standard error, and upper and lower confidence bounds. And one nice thing that we can do then is we can add those in. If we make our forest plot as before, we can now use the add poly function to add in the predicted values and their corresponding the corresponding uncertainty in those. And so with this one extra line of code, we can overlay these particular plots at minus 2%, 0, 2%, and 4% increase in the percent change from baseline and placebo, as well as the mean predicted the text representations of those. We can see as we move farther away from the mean, as we get, just as we see in normal linear regression, the farther you get from the mean of the covariate, the mean of the covariate distribution, you get wider and wider uncertainty bands. So we see a larger uncertainty here at 4% than we do here at 0%, which is closer to the mean of those six covariate values. Okay, so what we've done so far is really framed within the maximum likelihood framework using some of the functionality built into the metaphor package. The next thing that we're going to do is move into fitting this same model using WinBUGS. So it might be a good place to, again, pause for any questions. Okay. So let's move on to fitting these models in WinBUGS. Again, I've used the functionality in in the R to WinBUGS package that allows me to write my model as a function. And that's what I've done here. Alternatively, I could have written this in a text file and kept that separate from my R code if I wanted to do it that way. And like we said before, as we get into more complex models, that's going to be how we'll tend to work. But in this case, our model says the following. We're going to define the model as looping over our n studies. For each study, we have some data that's theta hat. And so we'll have a vector theta hat indexed by I. So I is 1 to 6 in this case. And we'll say that each data follows a normal distribution that's centered at a value of mean theta hat of I and has precision prec theta hat I. That part is very similar to what we had with our simple meta-analysis model. Now we'll say that the mean of theta hat I, whereas before that was simply defined as theta of I. Now we'll define this as our mean of theta I is alpha I plus beta times, in this case, I've standardized the covariates to xi minus x bar. So in this case, the individual study level predicted value alpha I will be the predicted study-specific value for a covariate value of 0. Then we say that the alpha i's in this case come from a normal distribution with mean alpha and between study precision of prec. And then this is just converting what I'll be passing in, the data I'll be passing in as SI, which is the standard error of the difference. And this is just converting that into a precision. So the POW function raises this value, SI, to this power minus 2. And that's how we're converting that standard error to precision. So all of this really defines essential elements of the hierarchical model. This bit of the code down here is simply defining prior distributions. So the prior distribution for mean alpha I set as a normal that's centered at 0 and has a precision of 10 to the minus 4, or a variance of 10 to the 4. If you want to think about it as a variance, or a standard deviation of 100. I put the same sort of prior on beta, and for tau, which is my between study standard deviation, I have a uniform distribution from 0 to 100. And then this last line just converts that between study standard deviation into a between study precision, which is the way that WinBUGS formulates its normal distributions. So that's really all there is to the model. We've made really the most fundamental changes here, simply saying that the mean for each study is now not just centered at the same population mean, but now that the study-specific mean depends on this covariate value xi. So let's go ahead and define that function. The data then that I'll pass into it is similar, really the same as we had before. I have theta hat is the diff variable from my Tour 80 data set. The S variable is the standard error of the difference. In this case, my covariate X is the percent change from baseline in the placebo group. And X bar is just the mean of those. We could do something fancier in taking a weighted average, but in this case, I'll just take a simple arithmetic mean. And then the number of studies is just the number of trials I have, or the number of studies. Go ahead and define our bugs data list object. The parameters that we'll monitor are mean alpha, that's like the intercept in our meta regression, or the overall population intercept. Tau is our between study standard deviation in that intercept. Beta is the covariate relationship between the covariate and our outcome. And mean theta are the study-specific mean theta values, accounting for both the between study variability in alpha as well as the regression piece. So we'll go ahead and say we want to monitor or define those parameters in that vector, and then write a function that generates initial values for our Markov chains. In this case, I'm just going to choose alpha mean alpha is coming from a normal distribution centered on -20 with a standard deviation of 20, and beta is coming from a normal distribution centered at 0 with a standard deviation of 1, and tau from a uniform 0 to 5. So this will give me some dispersion in my initial values for the Markov chains. And then this little bit of code here is going to go ahead and fit it for us. Again, we pass in the arguments here are data, and we tell it what the data object is we're passing into bugs, a function that's generating our initial values, what parameters we want to monitor, where our model is. In this case, I'm passing in the function, but as before, we can just point this to a text file if our model's in a text file. And then the number of chains, the number of overall iterations, and the number of iterations that we'll use as burn-in. So I'll go ahead and run this. I've set the iterations here to 30,000 and the burn-in to 5,000. So it'll take a minute or so to run. But what we should get out on the end is 3 Markov chains with 20,000 samples from each. So about 60,000 samples. And then we'll look at what we get for effective sample size in just a minute. Let's use our diagnostics here quickly to look at whether our chains are mixing well and what kind of indication we might have for autocorrelation in our chains. So and we'll do that first by just looking at these trace plots. So here's our trace plot for tau. It looks like the 3 chains are plotted here as green, red, and blue. And they all seem to be mixing fairly well. Similarly, for each of the mean thetas, are these nice looking caterpillar-like plots here. So we look at mean alpha. Again, mean alpha, the chains seem to be mixing well. There's maybe some spikes here towards fairly large values of mean alpha. But the chains do seem to be mixing well, also for beta. So overall, it looks like our MCMC is performing pretty well. That a burn-in of 5,000 seemed adequate for this particular model. And so we should be in pretty good shape. Let's look at what we get back if we print that object. When we print this object, what we get is some high-level summary in terms of posterior means, posterior standard deviation, posterior quantiles. Our hat here is the Gelman-Rubin-Brooks diagnostic. Again, we want that to be close to 1. That would be indicating that there's very little between chain variability relative to the combined between and within chain variability. And then this NF is a rough measure of the number of effective independent samples that we have. So remember here we have about 60,000 Markov or MCMC samples, but for some of these parameters, we have, for mean alpha, we have roughly equivalent of 46,000 independent samples. That's pretty good. But for our, something like tau, there's more autocorrelation in the Markov chain, so we end up with only about the equivalent of about 1,700 independent MCMC samples. But hopefully for our purposes of for summarizing things at a fairly high level, that should be adequate. We could, of course, look at a variety of plots, and we could overlay some predictions like we've done here from a Bayes model. What I thought we would look at, though, really first or primarily is how do the results from fitting this in the Bayesian context compare to what we got from RMA? So in RMA, we fit a maximum likelihood, and we ended up with a model here, fit4, that gave us a point estimate of minus 57, and a point estimate for the covariate relationship of minus 1.25. And if we look at the mean and posterior mean of beta, as well as the 2.5 median and 97.5 percentiles, you see that the posterior mean for beta is minus 1.24, so that's quite close to what we get for the maximum likelihood estimate. If we look at our confidence interval for beta, we had an interval of minus 2.5 to essentially 0. Whereas if we look at the credible interval, 95% credible interval from the Bayesian fit, we get minus 3.3 to 0.86. So it seems like a fairly substantive difference in the sense our Bayesian credible interval is noticeably wider. There could be a number of reasons for that. One of which is that these intervals are conditioning on the estimate of tau squared. So they're treating that as known. When we have, in this case, we only have 6 studies, so our estimate of the between study variance has a relatively high degree of imprecision. And so a lot of uncertainty, and the Bayesian interval accounts for that in the credible interval. It could also be due to the prior distribution that we used. So really, it would be worth exploring in this case, or if you're doing something like this in real life, to look at do a sensitivity analysis to your choice of prior. So we started out with a prior distribution that was normal with a mean of 0 and a prior standard deviation of 100. And at the end, we end up with a distribution that's fairly normal. Let's plot it and see what it looks like. We plot the density of REBUGS1 $sims.list $beta. If you look at that plot, it's roughly normally distributed with a posterior standard deviation of, let's see, of what? Roughly posterior standard deviation of about 1. So we've gone from a prior that's centered at 0 with a standard deviation of 100 down to a posterior that's centered at minus 1.24 with a standard deviation of 1. So it's possible that some of the extent of these tails are attributable to some extent to a very wide prior. But if you're interested in exploring the sensitivity of that to the choice of prior, I'd encourage you to do that. Let's come back and see if there are any additional questions on fitting these models in the Bayesian context. What I didn't do for this particular homework was have us work through the binomial example. And that's largely because we didn't really find any between study variability in the initial analysis. So it didn't really make sense to follow up with any meta-regression to describe that between study variability. But the way that you would extend a binomial model is very similar in the way that we extended this continuous model in terms of centering. In that case, you'd be centering things on the logit scale around a regression coefficient. Or I'm sorry, around a predictions based on a covariate. Okay, well, I don't see any other questions coming up. As always, feel free to post them to the course website. And we will be having a lecture this Wednesday. Bill's going to continue on with our work in model-based meta-analysis and getting into to fitting that some of those models with WinBUGS. So we look forward to talking with everybody on Wednesday, and I hope you have a good week. Thanks a lot.